everybody. We are studying Chapter 9 on chemical compounds. We're just starting this chapter today from BJU Chemistry's 5th edition. The first thing I want to talk about is from section 9.1, and I'm breaking this up into a couple of videos. So this is video A for ionic compound formulas. Our objectives today are going to be to determine the oxidation number of atoms and ions in an ionic compound, and then to use those oxidation numbers to write formulas for ionic compounds when given the elements of which they are made. So an oxidation number is the number of electrons an atom in a compound must gain or lose to return to its neutral state. If the oxidation number is negative, the atom has gained electrons, it is more electronegative, and this would apply to the nonmetals. If an oxidation is positive, the atom has given electrons, it is less electronegative, and this usually applies to metals. So the rules for oxidation numbers. There are 5 main rules, but rule number 4 has a lot of sub-rules. Rule number 1 is that free atoms have an oxidation number of 0. An example is if you just see Fe iron, its oxidation number is 0. The same would apply to sodium, argon, and helium, especially because they are noble gases, so noble gases have an oxidation number of 0. And the diatomics are all 0 as well. H2, O2, N2, F2 are all 0. Rule number 2 is that ion charge equals the oxidation number. For example, bromide with a negative charge, its oxidation number is -1. And magnesium ion with 2 positive charge, its oxidation number will be +2. Rule number 3 is that the compound sum equals 0. And I covered this too when we were doing the Lewis structures with the ionic compounds, that we had to make sure that the charges canceled out. So an example would be sodium chloride. For sodium chloride, we can break that up into the sodium ion and the chloride ion. Sodium is positive, chloride is negative. So +1 oxidation number because it takes the charge of the ion. -1 oxidation number must equal 0. Something a little more complicated, magnesium chloride. Magnesium ion has a +2 charge. The chloride ion has a negative charge, but there are 2 of them. So a +2 plus 2 -1s is +2 plus -2 equals 0. So always these cancel out to 0. Now, we're on to rule number 4, and these are like the special cases, okay? So there are a number of subsections to this. So group 1, our alkali metals always have a +1 oxidation number. So for example, lithium, its oxidation number is +1. Group 2 has a +2 oxidation number. So calcium, +2 charge on that ion, and its oxidation number is +2. Now hydrogen can be +1 or -1. It's +1 if it's bonded to a nonmetal, for example HCl, because the hydrogen will have a positive, the chloride ion will have a -1, and that balances out to 0. It will be a -1 if bonded to a metal. For example, sodium hydride. +1 plus a -1 for the hydride ion equals 0 because they have to cancel out. And sodium, we just learned, belongs to group 1, so it has to have a +1 oxidation number. Oxygen can be -2 or -1. Most of the times it's going to be -2, but I'll show you the case where it's -1. So water, for example. Water, we know that the hydrogen has a +1 because it's bonded to a nonmetal. So 2 positive 1s, that means the oxygen must be -2 to cancel out to 0. The exception is when it's in the peroxide ion, O2 with a -2 charge. So we know that because hydrogen is bonded to a nonmetal, that its oxidation number is +1, and there are 2 of them, so that gives us a +2. So the oxygen, since there's 2 of them, must be 2 -1s to balance out to 0. That's how we figure that out. Group 17, which are halogens, are always -1. So an example is hydrogen fluoride, +1 for the hydrogen because it's bonded to a nonmetal. So the fluoride must be a -1, and we know that halogens always take on 1 electron. So that balances out to 0. And finally, rule number 5 has to do with polyatomic ions. It says that the sum of the oxidation numbers in a polyatomic ion equals the charge. So the example is OH, the hydroxide ion. We know that the oxygen is -2, the hydrogen is +1, so -2 plus a +1 is a -1, which in fact does add up to that -1 charge on the polyatomic ion. Now, sometimes the oxidation numbers, elements can have multiple oxidation numbers. And the reason for this is the oxidation numbers of phosphorus, nitrogen, and sulfur are positive in some compounds and negative in others, because if they bond to more electronegative elements, they will have a positive oxidation number. And if they bond to less electronegative elements, they will have a negative oxidation number, a lot like the hydrogen case there. So those, and I'm going to show you on your periodic table where you can get oxidation numbers from as well, and that's why there are multiple oxidation numbers. So we're going to write ionic formulas using oxidation numbers and the crisscross method. So the first one is barium and iodine. And what we do is we write barium and iodine with its oxidation numbers as superscripts. We write it as if it's an ion. And so barium, if it's an ion, is 2 positive, and iodine is -1 for its oxidation number. That will be the charge on it. The next step is to crisscross. Okay, think of my shoulders as those charges. I'm going to crisscross them and drop them to the opposite corner, basically, next to the symbol for the other atom. And I'm going to take the absolute value of it. So this is what I mean. I have crisscrossed. The 2 that was up here is now low, below the iodine there. The 1 that was here is down here now. So I have crisscrossed them, okay? But in our formula units, we do not write 1s, so I have to simplify this to BaI2. Let's take a look at another example. Let's do this with calcium and oxygen. Again, I write these as their ions with their oxidation numbers. So calcium is 2 positive because it's in group 2. Oxygen is 2 negative. It would only be the -1 if it was the peroxide, and that would have a 2 down here and still the 2 negative up there. So don't get confused with that. If it's not peroxide, it's -2. And now we're going to crisscross. So we drop those numbers next to the opposite atom as a subscript. When we crisscross, we end up with Ca2O2. But remember, these are formula units. These are actually, it's in that crystal lattice structure, and there are billions of these together. So we must reduce this to its simplest ratio. And when I do that, I simply write it as CaO, calcium oxide. This is called a binary compound. These are ionic compounds containing only two compounds. Let's take a look at a polyatomic ionic compound. So we're going to now use our polyatomics, and this is an ammonium ion and a phosphate ion. So here I write the ammonium ion, NH4, with its positive oxidation number, +1, and phosphate, PO4, with a -3 oxidation number. Now I have put the parentheses around the polyatomic ions to show that the subscript that we're going to write next to each one applies to the whole ion. Otherwise, it would just apply to part of it. So again, I crisscross, and this +1 charge, the 1 gets dropped behind the parentheses behind the phosphate so that it covers the whole polyatomic ion. The 3 drops here behind the ammonium ion's parentheses to show that it applies to the whole ion. And I could rewrite this as NH4, 3, PO4, 1. But remember, we don't write ones. So I would rewrite this as NH4 with the 3 outside of the parentheses. I get rid of the parentheses for PO4 because there's no subscript behind it, and I just write it as PO4. And we understand that when we see that it's a polyatomic ion. So here I have a copy of your periodic table, and you can see there are selected oxidation states. So these are the oxidation numbers. These are the possibilities for each element. And one thing, you notice that carbon has multiple. Usually carbon doesn't form ionic compounds, but the most common one is at the top. And so if we take a look over here, for instance, we talked about the groups and the oxidation numbers. And so +1s for the most part for group 1. Hydrogen has a +1 or a -1. It's usually +1, so that's on top. For group 2, +2. We'll get into the transition metals a little bit when we're naming, and I'll tell you about those. Those have lots of multiples. Over here, +3 for the most part for group 13. And we said group 17, mostly -1. That's why the -1 is on the top. There are other possibilities. We also said for the noble gases, 0, right? So those have zeros for those. So that's where you can also find oxidation numbers. On the second page of your periodic tables, just inside the front cover, you're going to find your selected polyatomic ions in table E. Now, these are the polyatomic ions I will hold you accountable for. Their name is over here on the right. Their formula is here, and their oxidation number is the charge on each of them over here. This is the charge that they have as an ion, and remember, the charge is the oxidation number. And so this is what you will use for your oxidation numbers and writing your formulas. So our objectives today were to determine the oxidation number of atoms and ions in an ionic compound and write formulas for ionic compounds when given the elements of which they are made. Now, I do want to point out that one way you can find the oxidation number when given the compound, the ionic compound, is to simply uncrisscross. Okay, but you also have to be careful when you have those cases like calcium oxide that you remember that the calcium has a +2 and the oxide a -2. So there are some tricks to it, but a lot of times you can uncrisscross your crisscross when making the formula. So don't forget your 5 questions in your notes, and I'll be back with more videos about compounds.